Hi everyone, Kevin here, back with video number 2. We're looking at sugars in grapes. We have looked at the straight chain version of aldohexoses in the prior few slides, but most carbohydrates in solution exist as the cyclic form. In wine, about 95% of the sugars are in rings, the cyclic form, rather than straight chains. And the cyclic form is more stable, and that's why. They will interconvert. There is an equilibrium, but it's heavily weighted toward the cyclic form. And so in this slide, you can see the straight chain, and you can see that you can also represent that as sort of as shown here as almost a circle. In this case, the hydroxyl on carbon 5 is near the aldehyde group containing carbon 1, and the arrows show the start of a cyclization reaction. Here's that full reaction. So we have the attack of an alcohol on an aldehyde, basically. Now, this is an intramolecular nucleophilic attack, but we've got carbon 5, the lone pairs on carbon 5, attacking the carbon at carbon 1, the aldehyde carbon. Now, note the partial charges. Remember the partial charges. Very important in a carbonyl group, as is shown here. The oxygen is much more electronegative than the carbon, so it draws the electrons toward it. So the electrons are weighted toward the oxygen in this double bond here. So we have a partial negative charge on the oxygen, a partial positive on the carbon. So that makes that carbon in the aldehyde a good electrophile. And the hydroxyl group here is a nucleophile, relatively weak, but still a nucleophile. And therefore, especially when it's bent around, as is shown in the middle here, and we have the hydroxyl in close proximity to that carbonyl carbon, that facilitates attack on the carbonyl oxygen. And you end up losing this hydrogen here and forming the ring structure. All right, so that's the cyclization reaction. And note that this is a hemiacetal, and we'll talk about what that is, and we'll do a little review here in just a sec. All right, but that's the cyclization reaction. It is a hemiacetal, and hemiacetals are compounds resulting from the reaction of one alcohol and a carbonyl group, either an aldehyde or a ketone. So the basic structure, the basic reaction is shown here. You've got, in this case, an aldehyde, right? If this was an R group at the hydrogen that I'm circling now, this would be a ketone, but we're showing an aldehyde here. And here's an alcohol, right, with that hydroxyl group on it. If the hydroxyl attacks the carbonyl, we form a hemiacetal. To recognize a hemiacetal, look for a carbon bond bound to two oxygens, but one of those oxygens is in a hydroxyl group. All right, the other oxygen has some R group attached to it, but one of the oxygens is simply a hydroxyl group. So that's a hemiacetal. So let's look at the mechanism of formation of hemiacetals. Let's start with our aldehyde or our ketone. And the start of the reaction is often acid catalyzed, especially in wine. Wine is pH 3 to 4. We have high acid, relatively high acid, and so we often have acid catalyzed reactions. So in this case, the reaction starts with protonation of the carbonyl oxygen. All right, so we pick that up, and now we have a positive charge there that again increases the pull of the electrons toward the oxygen and away from the carbon. So it increases the amount of partial positive on the carbon and partial negative on the oxygen. So we've primed this for a nice reaction. So then our alcohol comes along. So our alcohol here and the lone pairs, which again are not shown on this oxygen, but we can draw them in. One of those lone pairs then will attack that carbonyl carbon as shown with the arrow pushing there. And will form a bond to that carbonyl carbon. So here's our new bond. And the final step in the process is removing that hydrogen, which can go back to a water in the solution. And we end up with our hemiacetal that looks like that. All right, and we can recognize it again. It's a carbon bound to 2 oxygens, one of which is in a hydroxyl group. So that's a hemiacetal. All right, that's our generic hemiacetal. Now let's go back and look at what that looks like with the cyclization reaction. And it is the cyclization reaction of glucose is shown at the bottom here. So just like in the well, what's not shown here is the protonation of the carbonyl in glucose, right? We showed the protonation here at the top in our generic mechanism. The same thing can happen in the cyclization of glucose. It can start with a protonation of the carbonyl oxygen that I'm circling now. But that protonation is simply not shown in this rendering of the cyclization of glucose. Then the next step, where the alcohol is going to attack the carbonyl, in the case of our glucose, we saw before, attacked by the hydroxyl on carbon 5 on the carbonyl carbon, that is carbon 1, to form the cyclic structure. All right, so it's similar to at the top, we had the attack of the alcohol on the carbonyl, and we formed the hemiacetal here at the top. We've formed a hemiacetal in the form of cyclic glucose at the bottom. All right, and we can see it again because that carbon is bound to 2 oxygens here and here, one of which is in a hydroxyl group. So that's our hemiacetal. Thanks for watching. That's it for video number 3. We'll pick up more review in video number 4. See you then.